This project compares traditional machine learning models, specifically support vector machines and k-nearest neighbors, with a convolutional neural network for the task of speaker identification. The aim was to investigate which approach would perform the best for speaker identification on a small dataset. The dataset consisted of 5 speakers, each providing 5 recorded speech files for a total of 25 samples. To expand the dataset to make it more suitable for training, I applied voice activity detection to isolate voice regions and remove silence. These segments were then split into 1-second clips, provided they exceeded a set loudness threshold. This increased the dataset to over 180 usable audio segments. The table seen shows how the segmentation varied by speaker depending on how much usable speech segments was present. For traditional machine learning models, I extracted a wide range of features using LaBrosa. These included MFCCs, delta features, spectral centroid, bandwidth, roll-off, contrast, flatness, zero crossing rate, chroma, and RMS energy. For each segment, I included the mean and standard deviation of each feature, resulting in 128-dimensional feature vectors. To reduce the dimensionality and avoid overfitting, I applied principal component analysis, which reduced the features from 128 dimensions down to 54, whilst preserving 95% of the variance. This helped both SVM and KNN train more efficiently and generalize better. Both SVM and KNN were trained using stratified 5-fold cross-validation. For SVM, I tuned the kernel type and the C and the gamma values. For KNN, I used different types of values of K and both uniform and distance-based weighting. Hyperparameter tuning was done using grid search, and the best models were then tested on a held-out 20% test set. The SVM achieved 98.9% test accuracy, whilst the KNN reached 96.2%. Classification reports and confusion matrices showed very high per-speaker precision and recall, with minimal confusion between speakers. For the CNN, I used MEL spectrograms as 2D inputs, with 128 MEL bands and a time resolution of 86 frames. The network included 2 convolutional blocks with batch norm, ReLU activations, max pooling, and dropout layers, followed by 2 dense layers for classification. The model was trained using a 20% validation split, with early stopping and model checkpointing to prevent overfitting. Training accuracy reached 100% within 7 epochs, but validation accuracy plateaued at 70% around epoch 15, indicating that after this it would start to overfit due to the limited dataset size. Early stopping helped to limit further degradation, as seen by the relatively aligned training and validation loss curves. I used UMAP to project the PCA-reduced features into 2 dimensions. The resulting plot shows distinct clusters for each speaker, which explains why the SVM performed so well. It was able to place effective decision boundaries between clusters. KNN also performed well, but was more sensitive to overlaps in the feature space. The CNN did not benefit from these handcrafted features and instead had to learn from raw spectrograms, so its confusion matrix shows that it learned to separate speakers by gender, but often confused speakers within the same gender group. The final test accuracies clearly show the SVM and KNN outperforming the CNN for this task. With the limited dataset and the carefully selected features, the SVM and the KNN provided highly accurate classification. The CNN underperformed here, likely due to the small dataset, showcasing how it may not be the best choice for this. In conclusion, this project demonstrates that traditional machine learning methods of strong feature extraction and dimensionality reduction can outperform CNN models with small datasets.